This video is going to serve as an introduction to the basic gas laws. Before we talk about the different gas laws, it's kind of important to review a couple principles from kinetic molecular theory with respect to from ideal gases and things that real gases can do that are far from ideal. So we need to review a couple of statements from kinetic molecular theory that pertain to ideal gases, remember. So there were 5 statements that we discussed, and one of those statements that we're going to talk about now is that the particles themselves have little to no volume. Remember that the volume of a gas is created by the distance between them. So the other statement we're going to talk about is also that particles do not exert any forces on the other particles that they interact with. Again, because they're in constant random motion, they're moving so quickly that they aren't going to be able to interact with any of the other particles in any meaningful way. There are 2 situations where real gases will deviate from acting like ideal gases. One of those is high pressure, and the other one is low temperature. Real gases deviate from ideal behavior in high pressure conditions because there comes to a point where when you're compressing a gas, there's not enough volume or space between the particles to where the particles themselves will actually matter and have to be taken into account when you're talking about the volume of the gas. For low temperature situations, these would affect the particle forces because when the temperatures are low enough, particles are moving very slowly, and if they pass by each other at a slow enough rate, they are actually able to interact with each other. So that's another situation where a real gas would not act ideally. We're now going to discuss some of the things related to the basic gas law, or the ideal gas law. We discussed this gas law yesterday in the molar mass of a gas lab. So PV equals nRT is essentially the ideal gas law as it's known. And just to review what those units are again, your variables within that equation are pressure, volume, amount, particularly in moles, and temperature. So the unit for pressure, there are actually lots of units for pressure, which we'll go over in just a minute, but the one that we're actually going to use the most is not millimeters of mercury like we used yesterday. It's actually going to be atmospheres, which is abbreviated ATM. We are going to need to use volume in liters, amount is going to be in moles, and our temperature must always be in kelvins. For any of the gas laws to work, for you to use those formulas, you must convert your temperature to kelvins all the time. It's kind of important to note, too, I give you the gas constant R up here, but I just want to point out, because it's a little bit misleading, this is not a minus sign here in between these units. This is supposed to be like a dot for a multiplication. So again, remember that the unit for R is volume and pressure over the moles and the kelvins. So in this particular case, this R value is 0.0821, whereas yesterday we were using 62.4. The reason that those numbers are different are they still represent the same exact thing in that they represent the universal gas constant, but for this one, this R value is using the units of pressure for in atmospheres versus the one we used yesterday, which was using pressure units in millimeters of mercury. So it's just like saying that room temperature, which is about 70 degrees, is approximately 22 degrees Celsius. It's the same physical value, it's the same temperature, but because we're using a different scale, a different unit, then that number is actually different. We also used one of these other laws yesterday. We used Dalton's law of partial pressures with the molar mass of a gas lab. So just as a review, the total pressure of a gas mixture, remember this is always when we're talking about a mixture of gases, is going to equal the sum of the partial pressures of the gases that make up that mixture. So yesterday we were using the total air pressure as a sum of the dry gas pressure from the lighter that we collected plus the water vapor pressure on the surface of the water in the pneumatic trough that we were using to collect the dry gas in the graduated cylinder. One last law I want to discuss or go ahead and give you right now is the combined gas law. I'm going to show you how to derive this using another law. It's actually a derivation of the ideal gas law. Before we go and talk about deriving the combined gas law, talk about some different units of pressure first. So we saw yesterday that we can have inches of mercury, which we can then convert to millimeters of mercury. As I showed you with the R value just now, atmospheres is going to be probably our most common unit of pressure that we use, but you may also see a couple values called torr, pascals or kilopascals, literally meaning 1,000 pascals, and even something called bars. You'll see on your reference sheet that there's a conversion factor for most of these, and it's just kind of important to understand that they all just mean different measurements of pressure. So back to the applied ideal gas law. This is just taking PV equals nRT and setting them equal to each other for an initial and a final condition, hence the ones and the twos. So because you would have R staying the same on both sides, we can remove R from that equation because it would be constant and it would divide out. So using that same logic, we're going to actually derive the combined gas law now. The combined gas law simply states that you have the same amount of gas in either situation in your closed container. So you're not adding or taking away any of the gas that's involved. And this is going to be important to watch and understand as far as why we're doing what we're doing, because we're actually going to derive all of the other gas laws using this same exact process. So interestingly enough, if N stands for moles, and that refers to the amount of gas, then we literally can remove those two things from the equation, and then the stuff that's left over is going to be our combined gas law. So that means that our combined gas law we can write down as P1V1 over T1, that's 1, equals P2V2 over T2. And again, that's the ideal gas law derived for two different situations, but with the number of moles staying constant. Okay, we're going to do the same thing again. This time we're going to talk about a law where we have constant moles and constant temperature. So let's take these two things out. And that leaves us with P1V1 equals P2V2. So this time we're going to be talking about a law that involves constant moles and constant temperature. So that's going to give us P1V1 equals P2V2. Again, N and T are constant, so that's why we took those out of the equation. Okay, this is Boyle's law. It's kind of important to note that we'll be able to derive all of these laws based on remembering what's constant. So knowing the constants lets us figure out the formulas. Going back to Boyle's law specifically, we can talk about the relationship between these things based on how they would look if we graph them out. So as pressure increases, what's going to happen to the volume? If we plot pressure and volume on an axis, we'll see that as pressure increases, volume would decrease. So that's going to give us an inverse proportion. The next law we're going to look at is Charles' law, and that's going to be derived in a similar fashion, except this time our two constants for Charles' law are going to be number of moles and pressure. If we take out pressure from this equation, we get V1 over T1 equals V2 over T2. So when we look at Charles' law written out, we see that the proportion is the opposite of Boyle's law. We have, instead of multiplication on both sides, we have fractions on both sides of the equal sign. So as volume goes up, or as temperature goes up, the other one goes up. And if you think about it, the more that you have particles moving, the more space they're going to take up as long as the container can expand. So that means that if we plot the two, volume and temperature, then we will end up with a linear relationship, which is also a direct relationship. So considering that this law has very much similarity to Charles' law, then we should see that the proportion is going to be the same, this time pressure versus temperature, and we would have a direct relationship again. Okay, finally we're going to derive Avogadro's law, not looking at the previous applied gas law, but Avogadro's law. Avogadro was the man that basically discovered moles. So in this particular case, moles are not constant, but pressure and temperature are. So by deriving our formula, that means that V1 over N1 is going to equal V2 over N2. And if you think about it, if you add gas to a balloon or a car tire, then that given container is going to get bigger. So that one makes probably the most logical sense, I would think. but it is also a direct relationship. So now let's look at a couple examples of how we actually use these laws to solve questions. I do want you to understand the importance of why I'm showing you the way that I am is because these are the steps that you should be completing while you do your practice problems. I want you to always solve for a working equation and always show the plugin that you're going to be using, because that's the easiest way to help me help you figure out where you're going wrong. Okay, so in example 1, we have a sample of air with a volume of 4.2 liters at a pressure of 1.1 atmospheres. What volume would this sample of air occupy if we change the pressure to 5.5 atmospheres? So honestly, I would list the givens out first because that allows us to kind of figure out what's going on. So we have 4.2 liters. We are asking for the new volume, so that's going to be a question mark right now. Our pressure started at 1.1 atmospheres, and we're ending up at 5.5 atmospheres. So because this question doesn't say anything about the temperature changing, it doesn't say anything about us changing the amount of gas that we're dealing with, we can assume that those things are constant and that we are applying Boyle's law in this situation because we're only changing or watching the change between pressure and volume. So that's how you know, because only pressure and volume are being affected. Okay, so looking back at the table, Boyle's law is like this. But in this case, we are solving for V2, so that means we need to solve for V2 down here. In order to get V2 by itself, we need to get rid of this P2. So we would do that by dividing both sides. And so that means that V2 is going to be P1 over V1, or P1 V1 over P2. Okay? When you plug that in or plug the information into this question, you'll get V2 equals 1.1 atmospheres times 4.2 liters divided by 5.5 atmospheres. And that comes out to give us 0.84 liters. Noting especially that the way that you've set up your working equation, you have atmospheres dividing out and you're left with liters as your remaining thing that's not crossed out. So that should match the variable that you're solving for, in this case, V. So if you have liters left, you should be measuring or calculating volume. If not, you've done something wrong somewhere along the way. In this example, we're looking at a different gas law. So again, copying down our information, we have a gas that's initially at 75 degrees Celsius. So that's going to be my T1. You'll see why I'm labeling it this way in just a second. And it starts out at 8.6 liters. It's cooled under constant pressure, so we know that pressure is not changing. And its final volume is going to be 3.0 liters. What is its final temperature in degrees Celsius? So that actually might be something useful to write down. Okay, the reason that I just wrote T1 up at the top was because we actually need to do something first with all temperatures for any gas laws, and that's convert it to kelvins. If you look back on the front of your paper, you have the formula or the math to do to convert to kelvins, and again, you're just adding 273. So if you have 75 degrees Celsius, that is actually 348 kelvins. If you do not convert to kelvins, you will not get the correct answer because the Celsius scale has a negative portion to it, and the Kelvin scale does not. So the reason we need kelvins for gas laws is so that everything is on the positive side of a temperature scale. Okay, so because we have V's and T's in this, that means we're going to be using Charles' law. Because volume and temperature change. So that one, again, was the fraction, so V1 over T1 equals V2 over T2. And a very common mistake here is to rearrange this equation the wrong way. You have T2 on the bottom, which means that essentially what you need to do is a couple steps of algebra. You need to multiply both sides by T2, and that's going to give you T2 on top over here, and get rid of it there. And then you're also going to have to then multiply by the reciprocal of what's around T2 that you don't want anymore. So you could break that up into multiplying by T1 and then dividing by V1. It doesn't really matter to me, but ultimately you get T2 is going to be V2 times T1 over V1. So try that on your own. Make sure you can rearrange that because that one's one of the trickier ones. Whenever you're solving for temperature using Charles' law, it's easy to make an algebraic mistake. So again, we want to do that first because it makes plugging in everything with our units much easier, because if you don't plug in with units, it's not going to be 100% correct in my book. So when you plug in your values, you get 3.0 liters times 348 kelvins divided by your initial volume of 8.6 liters. Okay, so this value comes out to be 121.395349. So we're going to round that to 120 if we're going to be using proper sig figs. But remember, look at your units. You've gotten rid of liters, but you have kelvins. So that means that this is 120 kelvins. But the question originally asked you for temperature in degrees Celsius. So you need to undo your Kelvin conversion by subtracting 273 to get back to degrees Celsius. Once you do that and do the subtraction, you actually get negative 153 degrees Celsius as your final answer. Okay, finally, let's look at one last example before I let you try some on your own. In this example, we have an actual amount of gas, so we have 2.5 moles of carbon monoxide with a volume of 20 liters at 31 degrees Celsius, which is 304 kelvins, again, because I added 273, and I'm looking for the pressure of this sample. So if you have a set of conditions and not an initial or a final, and additionally you have P, N, V, and T just like you did in the molar mass of a gas lab, this is when you are applying the regular ideal gas law. Okay, so you have in this case P, N, V, and T. But you may be asking yourself, well, the equation is PV nert, PV equals nRT. Do not forget that R is a constant, and you should always be able to find that value or be given that value somewhere. I'm going to use the 0.0821 number today just to let you see how that one would work, but that means that my unit of pressure is going to be in atmospheres as a result of that. So if I'm going to be rearranging for pressure, then that means I basically just need to divide by V. So I'm going to have nRT over V, which is what I'm going to plug into. So I have, my 2.5 moles, my 0.0821 liters atmospheres over moles kelvins, and I ran out of space, kelvins. Okay, and then that's also actually times my temperature, which is 304 kelvins. So I'm going to squish that somewhere. Okay, we're going to divide all of that by our volume, which was 20.0 liters. And so when we do the math, again, remembering that I just ran out of space here because I write big on this, and this is all multiplied together and then divided by 20. Then then when we do that math, we will get the pressure in atmospheres, because if you look at your unit for R, you have temperature and temperature dividing out. We have liters on the bottom and liters on the top of a fraction, which means those are going to go away. Moles are going to cancel out moles, and that leaves us with ATM as our unit of pressure. So make sure that you write that as your unit when you are finished. Okay, and when we do that math, we get 3.1198, and because I had 2.5 moles, that means I have 2 sig figs, so we get 3.1 atmospheres as the final answer. So what I'd like you to do next is please go and try the problems that you have on your practice worksheet. It's broken up by the law that's being applied, so you at least know which law you're using. So at the very least, list your givens and write down the working equation solving for whatever you have, as a question mark in your list of givens. plug in your information, and then do the best you can with calculating. The things that I know may trip you up, especially are not remembering to convert your degrees Celsius to kelvins, and also if you have different units of pressure, you basically just need to make sure that your units of pressure always match, or that if you're using R, the units of all of your variables all match your R value that you're using. Okay? I hope that helps, and good luck on your practice.